In our last video, we covered what multi-node modeling is in Xendee and how it's different from single-node modeling. Now that we understand when to use multi-node modeling and its advantages, let's now dive into the essential components. In this video, I'll show you how to set up the different multi-node components in Xendee and how to create a distribution network with PowerFlow. To start a multi-node project, we can either enable the multi-node toggle from the setup wizard of a new design project, or convert an existing single-node project to a multi-node project. When multi-node is enabled, you'll see additional symbols become available in the Symbols tab. Let's look at this model of an airport to start building a microgrid network. First, we'll step down the voltage from the utility connection and then distribute power to the two terminals. From the symbols bar, I've added 3 separate nodes. I have designated one node as a feeder node, which is going to be responsible for distributing power throughout the network. Additionally, we have nodes to represent Terminal 1 and Terminal 2. Now we need to add the building loads for Terminal 1 and 2. From the symbols bar, I'm adding a building load icon and assigning it to Terminal 1. Once assigned, we'll see that this is just like our regular load setup page. Here, I've directly uploaded the electricity profile for this terminal. Then, I repeated the same process for Terminal 2, so they each have their own respective building loads. Now that we've added our two terminals' building loads, we need to connect them to the utility so that they can receive power. First, we need to step down the voltage from the utility connection so that the voltage is safe for the terminal buildings. From the symbols bar, I'm adding a 3-phase transformer and selecting the primary node as the utility connection. The secondary node will be the feeder. The primary side voltage has the utility connection's voltage. We need to input the secondary side voltage, which is the usable voltage we want to distribute to our terminal buildings. We also need to define the transformer's power flow specifications to be able to account for losses. In this case, I'm going to fill in my own transformer specifications. But if you don't already have a transformer picked out, you can use the Xendee sizing tool. Xendee sizing will select a transformer from the catalog that minimizes costs, subject to the power flow constraints. Now that we've stepped down the voltage, we need to connect the feeder to the terminals so that the power can be distributed. From the symbols bar, I'm going to click on the cable symbol to add a connection between the feeder and Terminal 1. Here, I'm directly selecting a cable from the catalog. Then, I'm repeating the same process to connect Terminal 2 to the feeder. Now that our two terminals are modeled and connected, let's add some distributed energy resources, or DERs. Let's say we want to find the optimal size of solar capacity and battery to install to help reduce costs. And we also have existing backup generators. On my Terminal 2 node, I've gone ahead and added solar. We don't know how much solar is optimal, so I set the technology decision to consider. I've also used the draw tool to estimate the available space for panel installation. On the feeder node, I'm adding a battery and setting it to consider. Here, I'm also adding the existing backup generators. I turn the toggle on for backup only, so these generators will only operate in the case of an outage event. To see how the generator will operate during an outage event, I've added a 3-hour outage event in August. In the Optimize window, we have to enable Consider Power Flow if we want Xendee to enable power flow calculations. Here, I'm setting a voltage minimum and maximum to make sure the system's voltage stays within its limits. Additionally, I'm enabling Consider Losses, so Xendee will consider these losses in the cost minimization optimization. Lastly, I'm enabling Consider Branch Capacity to enforce the capacity limits of the cables and transformers. If this is enabled, it's important to make sure that your cable's ampacity inputs and your transformer's rating inputs are appropriate. Otherwise, you will get an infeasible solution if not enough power can be transported throughout the network. A quick optimization tells us our optimal DER sizes, but let's focus on the power flow part of the reporting this time. When power flow is enabled, you will see several extra tabs in the report. The Balance of System tab tells us each line item that makes up our microgrid branch connections. If you had input the costs in the cable and transformer setup windows, this table will also show us the total cost. In the dispatch chart, we now have an extra drop-down menu that allows us to look at the dispatch for different individual nodes in addition to the aggregated view. Let's take a look at the Terminal 2 node where our proposed solar PV is installed. On an average July weekday, we see that all the solar PV generation is consumed at this node. The rest of the electricity demand is met by energy imported from the feeder, which is in turn energy imported from the utility connection. Now let's take a look at Terminal 1's dispatch. Remember that Terminal 1 doesn't have any DERs installed directly, so it receives all of its electricity from the feeder. Now let's take a look at our feeder node, which has our proposed battery and existing backup generators. On a regular day, we see that most of the energy is imported from the utility connection. In the peak evening hours, when electricity is most expensive, the battery is discharged to reduce the demand for utility purchases. Let's take a look at our feeder node's dispatch during the outage day. During the 3-hour outage period, the backup generator kicks in and discharges along with the battery. The power is then distributed to Terminal 1 and Terminal 2 nodes to power their demands. When power flow is enabled, we'll also get an extra tab called Power Flow. Here we can see our network voltages. In this result, there's no big voltage drops across our network, and our voltages stay within the voltage constraints that we set. We can also see our network's electrical losses in each connection. Lower on this tab, we also get power flow time series plots for voltage, active power, and reactive power. Similar to the dispatch charts, we can also change the view by node, as well as different months plus day type. Let's change the node view to utility connection and look at a typical August weekday. Remember that the utility connection acts as our slack bus, so it has reactive power to anchor our system. Let's check out Terminal 2, where our solar PV is installed. Since the solar PV doesn't provide any voltage anchoring, it doesn't have any reactive power. Additionally, it doesn't have a positive active power because the import from the feeder node is greater than the solar PV generation. Let's check out our feeder node, where our battery and generators are installed. The feeder node has active power during the evening times, which reflects the battery discharging during peak hours for utility demand shaving. As we saw, modeling in multi-node enables us to assign each load and technology to their respective physical locations. Combined with power flow, this lets us capture network losses, factor in voltage behavior, and ultimately design a more physically accurate and realistic microgrid. In our next video, we'll take a look at thermal modeling in multi-node. So stay tuned if you want to learn more about multi-node modeling in Xendee.